This video is a brief introduction to the different paths of motion charges can take when traveling in a magnetic field. We have three different cases. The first case is when the charge travels parallel or anti-parallel to the magnetic field. This situation would look something like this. In this case, the force exerted on the charge is zero, and therefore the acceleration of the charge is zero. And since there's no acceleration, this means that the particle remains at rest or at a constant velocity. The second case is when the velocity of the charge is perpendicular to the magnetic field. This is when the charge would feel a maximum amount of force. So let's look at this example. We have a magnetic field that is pointing into this paper, and let's look at these three positive charges. So the charges end up traveling in a circle as shown with the green line. The velocity vectors look something like this and point tangent to our green line circle. Since they are the instantaneous velocity vectors, we can apply the right-hand rule to the diagram, and we see that the magnetic field is pointing into the page, and we align our thumbs with the velocity vector, and we see that there is a force pointing into the circle. This inward force is what keeps the charge traveling in a circle. So to recap, whenever a charge travels perpendicular to the magnetic field, it ends up traveling in a circle. Let's find an equation to further describe this circular motion. We know that the net force is equal to mass times acceleration, which is Newton's second law. We also know that the force on a charge moving in a magnetic field is equal to qvb. We also know that the equation for centripetal acceleration is v squared over r. So we can apply these equations to our Newton's second law equation, and now we have this new equation. We can then solve for the radius, and this is the equation for the radius for the circular path a charged particle travels is equal to the mass of the charge multiplied by its velocity and divided by the charge and the magnetic field. So lastly, we have this third case, and this is when the velocity has a component that is parallel and a component that is perpendicular to the magnetic field. This may seem a little confusing, so let me visually show you what this looks like. So here we have a magnetic field, and then we have a charge that is moving at an angle to the magnetic field, and there's a parallel component and a perpendicular component for the velocity of the charge. When this happens, the charge ends up traveling in a helix, which can be thought of as traveling forward in a circular motion. So an example of a helix is kind of like a stretched out spring. So here's our magnetic field, and the charge would end up traveling in loops around like this in a helix manner.